Welcome, everyone. This is ECS seminar at Jagiellonian University. Last talk of the semester. Today we have a local speaker, Bartosz Walczak, and we will learn something about asymptotic dimension. Bartek.
Okay, thank you very much. The work which I'm going to present is joined with Robert Hickinbotham, Freddie Illingworth, and Piotr Wicek. It is about asymptotic dimension of graphs with excluded induced or fat minors. So let me first provide you some motivation why we are interested in this problem of bounding asymptotic dimension for classes of graphs and what asymptotic dimension is. From some like my point of view, what the motivation is. So there is a recently popular branch of combinatorics graph theory called coarse graph theory, which basically wants to study properties of graphs, some kind of large-scale properties of graphs. So, like traditionally, parameters or properties traditionally considered in graph theory are very local. So, for instance, the chromatic number of a graph can be large because the graph contains a large clique, but a clique is like a local structure, yes? And in coarse graph theory, we would like to see kind of properties of graphs that happen at all scales. So we look at the graphs from farther and farther apart, and we want to see how this graph behaves. For this reason, in particular, the properties which we are going to study are not properties like the definitions, for instance. They are not they are not defined for a single graph, like terms like asymptotic dimension. They are not designed for a single graph unless the graph that we are looking at is infinite. So we can define something like asymptotic dimension for an infinite graph or for a class of finite graphs. And it doesn't really matter which kind of point of view we take. Infinite graphs are slightly more general. We can always view a class of graphs as an infinite graph which has just those finite graphs, gathers them all together as separate connected components. Okay, and since we want our properties to be invariant of the scale that we are looking at, we are studying properties which do not change with respect to so-called quasi-isometries. So, for instance, in traditional graph theory, the properties that we study are invariant on graph isomorphism, like chromatic number of a graph or independence number, or some structures like minors and so on. They don't depend on they depend just on the isomorphism class. So here, let me put this first definition, what a quasi-isometry is. We want properties which will be invariant on that. So a quasi-isometry has two parameters, a multiplicative constant and an additive constant. We could use just one parameter which captures both, but they play different roles, so I think it's more intuitive to have them separate. So an MA quasi-isometry from between two graphs, it is a mapping from the vertex set of one graph into the vertex set of another graph with the following properties. So let me add one more thing. A lot of things in coarse graph theory can be said about graphs which have weights on the edges. This is a very typical setup to have weights on the edges, but we can also work with unweighted graphs, and in this case, like the weight or the length of every edge is equal to 1. But in any case, those weights or lengths, they induce a metric space on the graph. So the notion of a distance. And this distance will be involved in this definition here. So the quasi-isometry is such a mapping that, first of all, it doesn't change the distances too much. So for any two vertices UV in G, the distance in H between f of u and f of d is at least 1 over m times the distance between between uv minus a, and at most m times this distance plus a. So we have both multiplicative distortion possible. The distances may be changed a little bit by some multiplicative constant in both ways, and we have also additive distortion. Okay, so we can scale graphs and we can perturb vertices in some sense. So this is the first property, and also the second property that we need is that we are more or less covering all of that graph. So our quasi-isometry doesn't go only in some local place in that other graph, but it covers more or less everything. So for every vertex V in H, there exists a vertex U in G such that the distance in H between f of u and v is at most that additive constant A. Okay, this is the second property, and this second property is in particular important to know that if we have two graphs and there exists quasi-isometry with some parameters ma from the first graph to the second, then we can also go in the opposite direction, and we will also find a quasi-isometry from this graph to this. Maybe we just need to modify the parameters a little. But being quasi-isometric is more or less an equivalence relation, like morally. So we want to study properties which are invariant under this notion. By the way, this quasi-isometry can be as well defined for any metric spaces. There is nothing specific to graphs in this definition. We can put the same definition for metric spaces, and this is a standard way also to define quasi-isometry. So, what are the reasons to study something like this in graph theory more specifically? So let me tell you two motivations, which this is the way how I understand it. So let's assume that we have some metric space which behaves nicely. So for example, some manifold, some torus or some other shape, but this is a metric space in which we have a well-behaved notion of distance. So the distance corresponds more or less to the maximum length of a path between two vertices, whatever that means. Okay, so of course, when we allow infinite graphs, the metric space itself is an infinite graph because we can represent every point as a graph. But this is not very interesting because then this is a complete graph and the degree is also infinite or maybe even uncountable. So say that we would like to approximate the structure of this metric space by making some kind of a net, so some kind of a sufficiently dense set of points inside that metric space, which can be chosen greedily, for instance, in the following way that, okay, how can we greedily choose this kind of set? If there is a point in our metric space which is far away from any point here, then we add it to our graph, and we keep repeating this kind of thing, and then we choose some threshold distance, which is, I don't know, something like 3 times this threshold for putting new points. And we are basically adding an edge whenever 2 points are at most at this distance. And in that case, we don't even need to assign lengths. We can consider this graph just a graph without any weights. And this graph will represent the structure of this metric space. Okay? However, we are free to choose the scale. We can make those points denser or sparser, and we would like the properties to be preserved, regardless of what scale we choose. So this is how, this is what's like this multiplicative constant here is responsible for, choosing different scales in quasi-isometry. Yes, so, okay, so basically we want that in any way we do, we obtain graphs which are quasi-isometric. Infinite graphs maybe, but they will be quasi-isometric to each other with some parameters. Yes, so multiplicative constant is responsible for the density, and the additive constant will be responsible for like kind of a perturbation. There is no fixed way of choosing these points. I could choose this point, but also I could choose this point here, and this will change the graph a little bit, but it will change it only with respect to these additive constants. So this is one kind of motivation for studying properties which are invariant under quasi-isometries. Another property comes from group theory. I don't know much about group theory, but for some reason, group theorists like to represent groups by graphs, so-called Cayley graphs. So whenever 2 points of so say that a group is finitely generated, so we have some finite set of generators, and whenever we have 2 points in a group, and one can be obtained from the other by multiplying by a generator, then they are connected by an edge in the Cayley graph. And somehow this Cayley graph is meant to represent the structure of the group. However, we can choose different generators. And we would like that the properties that we are studying are properties of groups themselves, not of that they will not depend on the choice of generators. And it turns out that if we choose a finite number of generators, then for the same group, then the graph that we will obtain will be always quasi-isometric to like the graph obtained with another choice of generators. Yes, so let's say that we are considering, for instance, Z, like our Z squared is our group with addition. Yes, so we have basically an integer grid, and one choice of generators will be these two vectors. Another choice of generators will be like this one, this vector, and this vector. So the first one will give us just a regular grid like this, and the second one will give us a skew grid, which will look like this.
The choice of generators changes M and A.
The choice of generators, yes. M and A will depend on the choice of generators, but for any choice of generators, we will be able to find such an M and A that it will be a quasi-isometric. Yes?
But if we are talking about finite graphs, then...
So, if we are talking about finite graphs, then for any two finite graph, we will find that we'll be able to choose parameters so that they are quasi-isometric. So this is why I'm saying that we should either think of infinite graphs or we should think of classes of graphs. And in the case of classes of finite graphs, we want to have quasi-isometry with some fixed parameter which depend only on the two classes. So we would like to know that, for instance, for every graph in one class is MA quasi-isometric to some graph in the other class and vice versa. Yes, so in such a case, we could say that two classes of graphs are quasi-isometric. I'm not sure whether this is a standard definition of defining quasi-isometry between classes of graphs, but definitely we can do this for infinite graphs, and then it still makes sense to have such a definition. Okay, so that would be it about motivation for studying quasi-isometry, like properties which are invariant under quasi-isometries. So, for instance, what would be an analog of chromatic number, which is invariant under quasi-isometries? So, like a coarse graph theoretic analog of chromatic number. So, it usually works like this, that if we want to translate some notion from traditional graph theory to coarse graph theory, then single vertices are replaced by some bounded radius balls, and non-adjacencies are replaced by being at distance at least some d. And since we want invariance on the scale, then we should have a property that for every d, so for every of this distance, something happens. So it will be the case that, usually the case that there is some function which represents this radius of balls according to the distances which, according to the number which tells us how far is far apart in our set. So let me show this to you, how it works in case of chromatic number. So we will be coloring vertices in our graph, and every color class, so every class of vertices with the same color, will be split into some number of clusters. And this partition should have the following two properties. That first of all, any two clusters will be at distance, say, greater than some d, any two of them. And the distance is always in the entire graph. Okay, but also the other property is that each of those clusters should have bounded diameter. And this bounded diameter is also computed in the entire graph, not just within clusters. Like a path which stays in the cluster can be very long, but we are interested in how far are pairs of points with respect to the metric of the entire graph. So this should be at most some, say, capital D, which depends on the small d. And that should be the case for each of those clusters. So every color class should decompose like this. And now we want to minimize the number of colors in this kind of a coloring. And then for like kind of historic reasons, which also has a nice geometric explanation, from this minimum number of colors we subtract 1, and this will be our asymptotic dimension. I will tell you in a moment why there is this -1. So basically, we want a minimum number of colors, so asymptotic dimension so say, let's say that asymptotic dimension is at most k minus 1. This is this -1, so we'll be using k colors. If there is a coloring of G, so either our infinite graph or every graph in our graph class for which we are defining the asymptotic dimension, with k colors, such that every color class, so if there is a coloring, but I forgot some quantifiers, so we should also write that for every D, there is a capital D of D, such that, and here I can, if we have a class of graphs, I can write that for every G in our class of graphs G, or G is infinite, then we just make a definition for the graph itself. Every color class splits into clusters of diameter at most capital D at pairwise distance greater than D. I hope that I didn't mess up anything in this definition. So it looks somewhat complicated, but first of all, it is not very difficult to convince ourselves that this definition is invariant under taking quasi-isometries. So if we have an infinite graph and another infinite graph which is quasi-isometric to it, then they will have exactly the same asymptotic dimension. Yes, the asymptotic dimension will be equal. Maybe we need to adjust this function d according to the parameters of the quasi-isometry, but this is everything that we have to do. the number of colors stays the same. Okay, so for instance, and by the way, we can make this definition also for a metric space. It doesn't have to be for a graph. We can make this definition for a metric space. So for instance, let's say that we want to color the plane just as a metric space. Then what we can do is we can take a hexagonal grid. Like so we can partition the plane into a hexagonal grid. For a parameter d that we have chosen. We want to partition it in such a way that the hexagons which are non-adjacent will be a distance at least d, but not much more than d, like that. And then the coloring would be like this: 1, 2, 3, 1. So now it should be 3, here 1, and so on. This should be 1, this should be 2, and so on. So 3 colors suffice if we do this kind of coloring. Yes, but the plane is intuitively 2-dimensional. Yes, so this is why basically the reason why we have -1 in this. That for instance, a d-dimensional Euclidean space will have asymptotic dimension d instead of d+1. If we have graphs like a grid and so on, then we will have the exact same situation. Yes, a grid will require 3 colors. Okay, so why are we interested in this asymptotic dimension? So first of all, there is this motivation coming from coarse graph theory. But also, it turns out that there is motivation coming, like this is a very similar to some structures studied by computer scientists. So, for instance, there is this definition is very close to something called padded partitions in computer science. So, a padded partition is a family of probability spaces on some cluster, probability spaces on some partitions of a graph. So basically, we want to, for every scale, say that for every scale delta, we want to randomly choose a partition of our graph into some clusters of diameter which is bounded in terms of delta. And we want to have the property that for every point, the probability that the ball of radius delta around this point in some graph distance, the probability that such a ball is fully contained in one cluster will be some positive constant, say 1/2. Okay, so the random choice is over all partitions, and we want that for every point, this probability is at least 1/2. So how can we obtain something like this from the clusters in the asymptotic dimension? So basically, if we are choosing k colors, and d is our scale, if we are choosing k colors, then we are choosing a color at random, but our cluster of the partition, it will be this one, which is enlarged by d/2. So this delta, which appears here, it will be actually d/2. And the rest, if some point is not within distance d/2 of any of these clusters, then we can make it like a single point partition and so on. So what happens now is that for every point here, each point gets some color in asymptotic dimension, in this coloring for asymptotic dimension. So if we are choosing the coloring, like the partition coming from a coloring at random, that with probability at least 1/k, actually exactly 1/k, we will choose like this color. And in that case, this enlarged partition, this enlarged cluster will contain a ball of radius delta centered at this point. Yes, so why is this useful? For instance, if this diameter of the partition is linear in delta, then it turns out that this kind of that this allows us to construct low average distortion embeddings, I mean constant average distortion embeddings of metric spaces into a line. And this is important for some approximation algorithms that construct separators for graphs. This is one of the standard techniques. So, which means that if we have this property where this control function here is linear, then we can translate it into those padded partitions which have linear diameter clusters, and this will allow us to construct those constant distortion embeddings. Yes.
Definition of padded partition. You need it for all delta, and that it holds this property.
Yes, for every delta we have some probabilistic space over partitions for every delta.
And the probability that the entire ball belongs in something, it's some constant.
Yes, it is some constant independent of delta, exactly. So usually we choose that this constant is 1/2 because there is a way of amplifying this probability arbitrarily high. Okay, but there is also, at least to me, there is a motivation coming from the studying the theory of chi-boundedness. So a lot of proofs in chi-boundedness or classes of graphs, they start by first showing that a class of graphs is what we call rho controlled. For some parameter rho, let's say at least 2, because if it is 1, then it turns out to be equivalent to chi-boundedness. And what does it mean for a hereditary class of graphs that it is rho controlled? It means that there is some control function such that for every graph in the class, if our whole graph has sufficiently large chromatic number, so chromatic number greater than some function f of k, then there will exist a vertex in our graph such that the ball of radius rho around this vertex will have chromatic number at least k. This is what rho controlled means. Okay? And now notice that asymptotic dimension, if we apply it to d equal to 1, just to d equal to 1, then it implies this property because we have a coloring with, like this coloring uses a bounded number of colors. Okay, let me maybe use a different constant here, L. This coloring uses k colors. So if we have a graph, if our starting graph has very high chromatic number, then at least one of these k color classes will have large chromatic number. At least the initial chromatic number divided by k. Yes, because the chromatic number of the union is at least the sum of the chromatic numbers. At most, the sum of the chromatic numbers, at most. So there will be a color class which has high chromatic number, but then this color class splits into clusters which are independent because we chose d equal to 1, so they are at pairwise distance greater than 1, they are independent. So if like all of them together have high chromatic number, then this is because one of them has high chromatic number. And this one of them has bounded diameter. So it will give us such a vertex that this ball of radius rho will have high chromatic number. And it turns out somehow that a lot of those proofs in chi-boundedness theory which show that some class of graphs is row controlled, they can be generalized to show that this class of graphs has bounded asymptotic dimension. Okay, so this is one more motivation for studying this. So let me introduce one more notion from coarse graph theory, which was recently very popular, which is the coarse analog of minors. So in traditional graph theory, a minor, say that we want to say that a K4 is a minor in some graph, then what does this mean? It means that we can represent every vertex of a K4 as some connected set, which is called a branch set. And those connected sets should have, between any two of them, there should be at least one edge somewhere. If we want to represent something like a diamond, like this, then, for instance, we don't require this edge, but we also don't forbid these edges. These edges are also allowed. So this is what minors means, and there is a very rich theory of graph minors. So, of course, there is this idea of a fat minor in coarse graph theory. So, a K fat minor, say again of K4, it will be something that looks like this. We again have these branch sets, but this time the branch sets are required to be pairwise at distance. I would like to write greater than K to be like consistent with all other inequalities which will appear, which are strict inequalities. Unfortunately, somehow it turned out that it's much more popular to define the K fat minor with a weak inequality here. But okay, so let me keep it like this, because this is the traditional definition. So all of them are required to be pairwise at distance at least K. And how do we represent the edges? The edges are represented as some paths which are connecting those parts. But we require that not just these branch sets are pairwise at distance at least K, but everything that I have drawn here is pairwise at distance at least K, except for the situation where we take a branch set and a path which ends at this vertex. So pairs of paths should also be at distance at least K. And if we have a path and a branch set which is not related to this path, then they should be also at distance at least K. So this is somehow necessary to avoid the situation that, I don't know, we have, say, a metric space which is very thin and looks like a star, but if we make sufficiently dense graph here, then we somehow can route a lot of edges through this very narrow space, but then it will not be K-fat. Yes, so still we will have the situation that for some K we will be excluding like a richer structure as a K-fat minor. Yes, so again we can convince ourselves that this notion of a K-fat minor is invariant under quasi-isometries. The only thing that maybe we need to change when we are going from a graph to a quasi-isometric graph is to increase the parameter K. So if one does not contain something as a K-fat minor, then the quasi-isometric one will not contain something as a K-prime fat minor. Okay, so here is a conjecture that maybe before stating this conjecture, I would like to I should say what happens when we exclude just as a minor, just any graph as a minor. Then the asymptotic dimension turns out to be at most 2. So we can like color with 3 colors, like the plane. And like, to be intuitively, this comes from the fact that if we have, say, imagine that we have, I don't know, a 3-dimensional grid, something 3-dimensional, because asymptotic dimension 3 means that we have something intuitively 3-dimensional. Then we have enough space to construct any minor, because we can use 2 dimensions, say, to, like, we can choose our branch sets to be anywhere we want here, and what? And we can use these other 2 dimensions to route those paths in such a way that they will not disturb themselves. And somehow intuitively also this should be a situation for fat minors, except that this is not known. This is an open problem. Okay, so an open problem is that for every graph H, the class of graphs excluding H, and maybe I should for every K, excluding H as a K fat minor has bounded asymptotic dimension. Actually, it is even possible that this bound is 2, but we don't even know whether there exists a finite bound. What we do know here is that, like, we know this for a lot of special cases. So, for instance, cycles, this comes from a work of Manning and was proved by Georgakopoulos and Papazoglou, like derived from this Manning result. Then we know this for K, like for stars, again Georgakopoulos, Papazoglou. Then K2T, for t equal to 3, this was by Chepoy, Dragan, Newman, Rabinovich, Paxes, and then in general by Albrechts and Lister, Georgakopoulos. Then we know for K4, which was done by Albrechts and Jacobs, Knappe and Wollan, for trees. And for trees, it was done by Nguyen, Scott, and Seymour. And I think that's it for all the cases. And in all those cases, actually, it can be proved, and this is how this result is shown for these is usually shown for these cases, that the classes of graphs which exclude this as a K-fat minor, they are quasi-isometric to the class of graphs which exclude the same thing as a minor. And since they are quasi-isometric, and for those we know that the asymptotic dimension is at most 2, actually for bounded triwids it's at most 1, and asymptotic dimension is invariant over taking quasi-isometries, then we have the same bound on the asymptotic dimension. Yes?
In the original conjecture, this bound depends on H and on K.
I'm not sure what is the first place to refer as the original conjecture. So there is a paper by Bonamy et al. Where they proved that the minor free graphs have asymptotic dimension bounded by 2. then what they assert is that there is a universal constant which works here for all graphs, in particular for all excluded graphs. There is also a conjecture in the paper by Georgakopoulos and Papazoglou. The conjecture there is that the bound on the asymptotic dimension is, I think, the number of vertices of h minus 2. It is supposed to match somehow the Hadwiger's conjecture, except that that conjecture is stated for something called Aswad-Nagata dimension, which basically means that this function d is a linear function without a constant term. This is how he states this conjecture. But there, in that conjecture, it depends on graph H. But he also writes that the bound as well may be 2, rather than this specific value that he put as a conjecture. Okay? What can we see from all of these cases is that they are planar. So we don't know of any non-planar graph for which this conjecture would be true. However, for all of these cases, the graphs under consideration are actually quasi-isometric to graphs which exclude the same thing as a minor, and it was also a conjecture in coarse graph theory that this always happens. So the class of graphs excluding H as a k-fat minor is quasi-isometric to a class of graphs excluding H as a minor. This turned out to be false. It is actually false even in but a much weaker conjecture is false. Namely, a weaker conjecture would be that for every H there exists H prime, such that if we exclude H as a k-fat minor, then we are quasi-isometric to something that excludes H prime as a minor. But this also turned out to be false. And what is interesting, this turned out to be false for a planar graph H, which is basically a grid of dimensions 154 by 154, and this is a result by Albrechtsen and Davies from last year, so that's a very, very fresh one. So we cannot expect this kind of reasoning even for all planar graphs. So our first result is that the conjecture holds for every planar graph H. Yes?
You know what the asymptotic dimension is? Like if it's 2, for example, or if it's more bounded?
I don't. Well, I know that it is bounded because of our result, but only because of that. So they showed that it is like whenever they have an infinite graph which excludes this as a fat minor, and it is quasi-isometric that to. I don't want to mess up quantifiers. Okay, let me back up. I don't want to say something wrong. So, but they showed that this cannot hold for this kind of a grid. Like not this, but the quasi-isometry conjecture. Okay, so here we show that this conjecture holds for every planar graph H. What else can we say? So there is a notion which is somewhere in between those fat minors and ordinary minors. Mainly we can speak of induced minors. So in induced minors, when we are looking for this as an induced minor, then actually we are forbidding these kind of edges. Whenever there is a non-edge here, then there cannot be an edge between the two branch sets. This is what it means that a minor is induced. So an induced minor is something very similar to a two-fat minor here. Yes, because this distance between branch sets is required to be at least 2, and those paths, they certify adjacencies whenever they are needed. But it is not exactly the same. Like induced minors and two-fat minors, they are not exactly the same, but they are very, very close. So we can ask the same open problem about the class of graphs excluding H as an induced minor, that it has bounded asymptotic dimension. And this is again an open problem. Okay, so another open problem, which is weaker than this, is that for every H, the class of graphs excluding H as an induced minor has bounded asymptotic dimension. So what we can prove is that this holds for every string graph H. String graph is an intersection graph of curves in the plane. So every vertex is represented as a curve, and two vertices have an edge between if the curves which represent those vertices intersect. So for every graph H which has such a representation, we have that when that graph H is excluded as an induced minor, then we have a finite bound on the asymptotic dimension. Okay? String graphs are broader than planar graphs in particular. Every planar graph is a string. Okay. So once we have this, I should also come back to this. I should still come back to this motivation that comes from the theory of chi-boundedness, because in the theory of chi-boundedness, there was something called Scott conjecture. Where can I continue? Maybe I can erase this quasi-isometry definition because we will not need it anymore. So for Scott conjecture, let me first write open problem. For every H, in Scott's conjecture, we were excluding H, like induced subdivisions of H. Or to say it different, we were excluding H as an induced topological minor. And the conjecture was that these graphs are chi-bounded, which means that the chromatic number is bounded always by some function of the clique number. So the only reason for a chromatic number to be large is that there exists a large clique, no other reasons. This turned out to be false because of a very specific construction called Burling graphs. However, there is still the following conjecture that for every H, how did I write it here? The class of graphs excluding induced subdivisions, for every H, there exists rho such that the class of graphs induced subdivisions of H is a rho controlled. This is a problem by Scott and Seymour. Rho controlled means that whenever we have large chromatic number, then there will be a ball of some radius rho with large chromatic number. Yes, this is the property weaker than asymptotic dimension. We cannot expect bounded asymptotic dimension here because the graphs of bounded degree have unbounded asymptotic dimension, and they exclude anything that has degree greater than 3. Say, the graphs of degree 3 have unbounded asymptotic dimension, and they exclude, say, K5 or anything that has a degree, like a star with four leaves, they exclude induced subdivisions of that. Yes, so we have this weaker conjecture here, and we have a recent result joined with Tara Abrishami, Marcin Briański, James Davies, Seeing Du, Jana Masaříková, and Paweł Rzążewski. Basically, the result says that whenever we have a class of graphs excluding induced subdivisions of H and row controlled, so if these two conditions hold, then the chromatic number is bounded. Like there may be only two reasons for large chromatic number: either large clique or large Burling graph as an induced subgraph. Okay, so this one construction which falsifies, which disproves Scott's conjecture. So this is something that we call Burling control. So if this conjecture holds, then actually every class of graphs excluding induced subdivisions of some H is not just row controlled, but it is Burling controlled. But now if we combine this result with this result, and with the fact that every Burling graph is a string graph, we obtain, as a corollary, a complete characterization of when an induced minor closed class of graphs is chi-bounded. So a hereditary, okay. If a graph is induced minor closed, then it is in particular hereditary. So an induced minor closed, which means that whenever we have a graph in a class, then every induced minor is also in the class. Graph class is chi-bounded if and only if it excludes some Burling graph. One direction is very easy, because if it contains all Burling graphs, then Burling graphs are not chi-bounded, so the class cannot be chi-bounded. However, if it excludes some Burling graph, and it is induced minor closed, then because Burling graphs are string graphs, then we can apply the fact that like this theorem tells us that the asymptotic dimension is bounded. Therefore, the class is row controlled for some row. And now, if something is excluded as an induced minor, then consequently also induced subdivisions of that something is excluded, because induced subdivisions are stronger than induced minors. So we can apply this result, this implication, saying that the class is Burling controlled. So whenever the chromatic number is large, then it is because either we have a large clique or large Burling graph. However, if we exclude some Burling graph, then we cannot have arbitrarily large Burling graphs, so the class has to be chi-bounded. Okay, so that would be it about the results. So let me tell you a little bit about how the proof goes for that. This is a definition of asymptotic dimension, so maybe I should keep that. So what can I erase? Maybe let me erase this. So the key graphs to look at is a class of graphs that are sometimes called pure to near in the literature, which means basically that they are intersection graphs of horizontal and vertical segments. Okay, say that we are looking at the class of graphs like that, and there will be a special role played by the horizontal segments, and a completely different role will be played by the vertical segments. And I'm going to assume that a graph like this is excluded. So say that such a graph H is excluded as a de-induced minor. So de-induced, it means more or less the same as induced minor. So what would be a de-induced minor? Whenever, say that we are looking for this as a de-induced minor. So whenever there is an edge here, there should be a corresponding edge here. However, if two vertices are not connected here, then we want these two branch sets to be at distance greater than d. So ordinary minors are 0 induced minors, ordinary induced minors are 1 induced minors, and so on. Okay, I was using d here, so maybe let me change this to r.
Between de-induced and d-flat is what?
The difference between de-induced and d-flat is that here we have direct incidences. So basically what we could do is we could even pretend that these kind of things are parts of that graph, like that. And with this kind of, this doesn't change a lot, this condition. It just changes this r to r minus 2 or something like that. We just need to make sure that we are not representing something like this. This would not be a good de-induced minor of K5. So we want to know that after removing any of that, these are basically leaves of that structure, that this is connected and these are just attached as kind of as a leaves. So if we look at those R-induced minors like that, then a K-fat minor is basically a one subdivision. So if this is our H, say that our H is a triangle, and we want to have this as a K-fat minor, then we are subdividing every edge once, and these subdividing vertices are representing our connections. Yes, because every path in a K-fat minor, every path was also supposed to be represented by a set. And whenever two of them were non-incident, the distances were also required to be large. Right? So basically, H as a K-fat minor is equivalent to one subdivision of H as an R-induced minor. So this is in particular how we prove this first result for planar graphs H excluded as a K-fat minor. Every planar graph has the property that if we subdivide an edge once, then it can be represented as an intersection graph of vertical and horizontal segments. So say every original vertex of H is a horizontal segment, and then every edge is represented by a vertical segment like this, which connects two segments. And every planar graph has this kind of a representation. Yes, so if we can prove this, okay, edge induced, then we want to prove that asymptotic dimension is bounded by something that depends, some constant which depends on h. So if we prove this for this kind of graphs, then we are getting as a corollary the result for planar graphs. How are we getting this result for string graphs? That when string graphs are excluded as induced minors. So basically, every string graph is an induced minor of such an intersection graph of horizontal and vertical segments, because we can represent strings, we can approximate strings by horizontal and vertical segments, like that. Right? And whenever two of such strings intersect, then a pair of these vertical and horizontal segments will intersect. And whenever two strings don't intersect, then no pair of segments from here and from here will intersect. Yes, so our string graph is an induced minor of such a intersection graph of horizontal and vertical segments. Okay. So how does the proof go? We proceed in two phases. I would like to keep this this definition of asymptotic dimension. So let me maybe draw the key structure here. So let's assume, that some h, which looks like this, is excluded as an R-induced minor, and the asymptotic dimension is sufficiently large for our purposes. So say, for instance, at least 2 to the power number of vertices in this H. Then we want to conclude that we will find the following structure in our graph. This structure consists of, imagine that this is some kind of a three-dimensional picture. We will have some number of paths, which I am drawing vertically, and that will be a huge number of paths. And now imagine that we have a lot of levels, like as many levels as horizontal segments here. And in each of those levels, there is a tree attached to all of these paths. Like that. This happens at level 1. And then there is yet another tree at level 2. And there is a connection to each of them. Each of these paths is connected by some branch to this tree. And so on. And we have a lot of levels like that. But we also need some distance assumption. Namely, a very important condition here is that if we are looking at this kind of level I, then one thing that we know, and say that we are looking at level I, so at tree number I and some of these paths which has number j, then this tree, it will have a branch which ends here. But we also know that these paths have some designated sections at the ith level, and only these sections can be close to this tree. Which means that every point in each of those paths, which is at a distance at most r, this r here, at most, if we have a point here, a point on this path, which is a distance at most r from this tree, then it has to be in this section. It cannot be anywhere else. Yes?
When it's assumption on the length of the section?
No, I don't have any assumption on the length of the section, but the sections at different levels are disjoint, and they come consecutively. So if we have levels 1, 2, 3, 4, and so on, then they come in this order. And then there are also more distance properties. So for instance, any two of these, they should be at large distance, like compared to R. Say, for safety, at greater than 3R. Okay? But also, any two of these should be at distance greater than 3R. And also, any two of these sections, even on one path, should be at distance greater than 3R.
When you say distance, it's in the whole graph.
Distance is always in the entire graph. Yes, the distance function is always with respect to the entire graph. So, one thing is to find this kind of structure when we are excluding H as an R-induced minor. And another thing is when we can find this structure. Okay, no, sorry. One is to find this structure if the asymptotic dimension is sufficiently large. That if the asymptotic dimension is sufficiently large, then we can find this. And then there is another part of the proof. If we can find this, then we can construct H as an R-induced minor. So what we would like to do to construct, let me first focus on the second part. So given this, we want to construct H as an R-induced minor. So the vertical segments will be represented as parts of those paths. Yes, so for instance, if the vertical segment goes between levels I and J, yes, so this is like, this is like level I, and this is like the last one is level J, then on each of those vertical paths here, we have those sections corresponding to all levels between I and J, and we take just that part between section number I and section number J to represent a vertical path. To represent a horizontal part, what we would like to do. There is some number of, say that we want to represent this segment here. So there is some number of vertical parts which we avoid because they end higher or they start lower. Okay, so first of all, where are we going to choose this? We are going to choose initially, like the initial try, is to choose some part of that tree. So if this is level J, so we are looking at a tree of level J, and we would like to choose some part of that tree to represent this horizontal segment. And we don't need to care about being at a distance D from these guys because they end up sufficiently high. So by the conditions of that, we are at great distance here. We also don't need to take care, okay, we have to take care of the fact that we should intersect these guys, this one and this one. So the way how we are taking care is that we are going to take this path, and we are going to take this path. So for instance, we would like to take these parts of the tree. What is the problem? The problem is that since this segment starts and ends somewhere, still we would like to be far away from the representatives of these vertical vertices which are entirely to the left, or these vertical vertices which are entirely to the right. And here we don't have that, because it could happen that some vertex here, it might be even adjacent to one of these paths. Needless to say that it might be at a distance less than d. Okay, so like this approach fails. If it didn't fail, we could just represent any graph we want. We wouldn't need to restrict to this pure 2D. However, what we can do is that, okay, we know that whenever such a vertex occurs here, then, so such a vertex which is at distance less than d from, say, this wire, this vertical path, then the set of vertices at distance less than d is only in this section. So how are we going to use that? We are going to use some kind of Ramsey type property. So basically, we are going to use, okay, so let me introduce the following symbol. So say that S level J, now I am taking some vertical path W, and I am taking some set of vertical paths, let's call them U, which can be to the left, to the right. So what is that? This thing is, I'm starting at the jth, I'm starting at W and going along the path towards the root of this tree, of this jth tree. And if I am never close to any of these vertical paths, here or here, then this will be some special symbol, let's say like bottom. And if I am at some point I become close, so at distance at most r to one of these guys, say I'm at distance r to this guy, then this one has, let's call it U, then this thing will be U. Okay, so I'm just recording the first one on this path that I'm being close to. It will be unique by the fact that I'm looking at distance at most r, and those paths were supposed to be at distance greater than, say, 3r from each other. So this first one will be unique. I cannot come, when I am close to one of them, I'm far away from all others. So by an appropriate use, so like the idea is that we are taking many more of these vertical paths that we initially needed, and by appropriate use of Ramsey's theorem, we will end up in the following situation, that I can have a group of, say, m plus 1, where m is the number of these, what is m? M is the number of these levels. A group of m plus 1 vertical lines, yet another group of m plus 1, and so on, yet another group of m plus 1, and so on and so on. I have as many groups as there are those vertical segments. Okay, so if this is n, then I have n of these groups. And now I want to have the property that if at level j, I want to embed a segment like this, which spans groups from, say, A to B. So it spans vertical lines from A to B. then I'm looking at here at groups less than A, so say that this one is group A, this one is B. I'm looking at groups greater than B. And now the property is that for every, at level J, for each of those chosen as W, for each of those, if this is my set U, this plus this is my set U, then they all give me the same small u. So the same one is the first one which comes close, regardless whether I start here or here or here or here or here or here or here. The same one will be the close. So how can I use this fact? I can use it in the following way. If these are the ones that I want to intersect, then instead of using this tree, I am coming to the vertex which is close to this guy. Say that this is the vertex, this is the vertex, this is the vertex which is close to this guy. And instead of continuing further here, I'm actually turning round and I'm extending my tree towards here. And I'm using this vertical path not for the purpose of embedding a vertical segment, but for the purpose of embedding the root of this horizontal tree. Instead of going further here, I'm turning and this will be my root. Okay? So now I have to exclude this guy, whichever it was here. I cannot use it for embedding the vertical one, but I have enough many in this group so that I can exclude one for every horizontal level, and there will be still one which I can use for embedding the vertical segment. Okay? But now, because this was the first one that I was close to when following these paths, then I know that I will not be close to another one less than A or greater than B. So we will not have this embedding problem which we had before. Okay, so this way we will find our graph H as an R-induced minor. This is more or less the idea. And let me use my remaining time to show you more or less what is the idea for constructing this thing. So let's assume that we start with asymptotic dimension, which is sufficiently high. So we have the property that for our graph, we need a lot of colors for this kind of cluster, for this kind of coloring by these clusters, which is written here. So if our graph is disconnected, we just focus on one connected component. We choose root arbitrarily. And we are going to do a BFS. We run BFS starting from this root. This BFS gives us a lot of levels. If the graph is infinite, we will just have infinitely many levels. Now, there is some d, like we also have set a parameter small d, like up front. And for this small d, we want to choose a capital D, which we can choose it as large as we want. So say that it is huge. So like I can cut off d, or say d half from the beginning, because all of that can be just one cluster of, and it will have diameter d. And now I'm starting gathering levels, and I'm looking at strips of size small d. Another strip of size small d. So this is like a group of d levels in our BFS. So if I need a lot of colors for this entire graph,
But if you assume that the asymptotic dimension is large,
I assume the asymptotic dimension is large.
that's why there exists D such that it's such that the witnesses that is large. Yes, so you fix
Yes.
that D, and then
For that D, I need a lot of colors.
any capital D doesn't work, so you fix a sufficiently large capital D.
Yes,
and
yes,
that's-
yes.
Yeah.
I'm taking sufficiently large capital D that my argument will work.
Yes.
So I'm here gathering groups of D levels, and since I need a lot of colors for the entire graph, then it turns out that if I restrict just to the sets in one of the levels, there will exist a group of these levels such that if I restrict just here, I will need at least half of that many colors. Because basically, if I'm coloring here and getting some bounded number of colors, then I can repeat the same colors distance D apart. And I can repeat the same colors here. Because the clusters which are here will be at distance D from clusters which are here. So I'm focusing on a level for which I need a lot of colors for that coloring. And also just one color is sufficient for this because this has bounded diameter. Yes? So I'm focusing on that. Then I'm taking kind of a neighborhood. This neighborhood has to be very precisely defined, but think of it that we have some slack. So I'm taking not just a D, but I'm taking D plus, say some capital R here, or some R1. Okay? And also I'm taking R1 here. And this will be a group of levels in which I'm repeating the BFS. So I'm running another BFS just inside here, or actually inside one connected component of that. But when running this another BFS, I track this smaller set, which actually I know that it requires a lot of colors. So when running, so in general, I will have the following situation. There is some set which we know that requires a lot of colors. I'm running a BFS in some neighborhood of that, and that sits somewhere in the entire graph. Okay? And this BFS is run with respect to the edges which are only within that neighborhood. So we could say that this BFS is with respect to the distances in this induced subgraph. But this is the only place where we are using distances in the induced subgraph to define this BFS. Otherwise, I'm going to speak in the distances in the entire graph. So this gets partitioned into some levels. However, we know that here there is this smaller set that we are tracking. But here again, we are taking groups of D levels, and so on. And now by the same argument, but just restricted to this set here, I'm going to take a level such that the coloring, in order to color this intersection in an appropriate way, I need a lot of colors. And then I will recurse again to run the BFS, but I will recurse where? I will again take some neighborhood of this thing to recurse on. But this neighborhood will be significantly smaller than this neighborhood that I had initially. So there is still a lot of slack between this border and this border. So in particular, what does it mean? It means that if I have some structures here, for instance, what would be the structures? That will be those trees. Those red trees in this structure which we are looking at, they will come by some initial fragment from some initial fragment of this BFS. And now, since this BFS is run in this neighborhood, it could possibly happen that we have some vertex outside of that neighborhood, which is a neighbor here, and then much, much lower, we have a vertex which is again somewhere here. So we can make shortcuts in our BFS going through outside. But what is important is that we will, with this kind of shortcut, we will never come inside this smaller neighborhood because there is this slack. Okay, so this structure will never be close. It will always be far from anything that we find inside the smaller neighborhood. Okay, so we keep repeating this many times. How many times? As many times as there are those levels, so those horizontal segments. And at the bottom level, we are getting some set which still requires many colors, say at least 2 colors. And if it requires at least 2 colors, then it implies that it has huge diameter in the entire graph. This huge diameter is at least capital D. So if it has huge diameter, then I can greedily find a lot of points which are pairwise at huge distance. This distance is huge. And now, starting from these points, I will be going up the recursive structure, constructing those vertical paths. And those vertical paths, they will have bounded size. The size will be bounded by some of those, by some function of these bounds which we are using for those neighborhoods. So think of each of these paths going up and being short. So if these paths are short and we start, like the beginnings of them are sufficiently far away, then the entire path will be sufficiently far away. We just need this starting point to be sufficiently far away, and then the whole path will be sufficiently far away. So it guarantees this condition that those paths here, they are separated. The fact that these trees here are separated comes from the fact that this tree, it will be some initial fragment of that BFS, and the next tree will be inside that neighborhood, and this is, like here you had the explanation that this will never close to anything which is inside that neighborhood. Okay, so I still need to tell you how exactly I am constructing these paths. So let's consider the situation that here those paths say that here there is this neighborhood in one of those BFSs which looks like that. We have that neighborhood here, and we want to grow these paths which come out somewhere from these vertices. So, okay, so say that this is the starting point, that we found those sufficiently far apart vertices. We go towards the root. To a level which is sufficiently far away from this thing. And once we reach this point where we are sufficiently far away from this whole thing here, we turn to the BFS at the previous level. So we are at some vertices like that, whatever remains here, this whole thing will be our bottommost, will be this, our bottommost tree in this structure which we want to construct. It will be our bottommost tree here. And here our path turns to the previous level. What does that mean? It means that these vertices which we ended up here, they are now somewhere inside that neighborhood. They are somewhere here. That may be lower, they may be higher, they are somewhere here. We are turning to go up. So in order to leave this neighborhood entirely, we have to make some number of steps, which is basically twice as large as the size, as the radius of this neighborhood plus d. So as we are turning here to this previous BFS level, we need to have gone sufficiently far away that when we are turning, we will not go back inside here before leaving this yellow neighborhood. Once we leave this yellow neighborhood, we are happy because we will never go back anywhere close here. But we should be sufficiently far away here because when we turn, we can actually go back in some sense because we don't control where this path goes. It could go away, it could go again closer to this, but if this distance is much larger than the height of this, then we will not go sufficiently close, and we will leave. So then we are leaving the yellow neighborhood, and we are going sufficiently high so that when we turn to the yet previous BFS level, we will not come any closer to this yellow neighborhood, and so on and so on. And this way we are also guaranteeing this property with those yellow sections, which are the only sections that can be close to the red trees. Namely, this yellow section for this red tree is somewhere more or less here. These are those yellow sections. Whatever is close to this tree in this BFS, plus distance at most d after leaving this neighborhood. Otherwise, we are already sufficiently far from this guy. And this is the way, more or less, we are finding this structure, which then allows us to find our segment, horizontal and vertical segments as a induced minor. Okay. Yes, so thank you.